I'm Gus Serino. I have a background as an engineer, control systems engineer. I did, design of process and automation for an engineering company. Then I worked for MWRA, which is a large water utility in Massachusetts, for 15 years as part of the team that automated the water and wastewater processes. The cybersecurity became a big, talking to the microphone. Should I start over? No. All right. So I'm just going to continue. So at MWRA, I was part of the team that was responsible for automating the water and wastewater systems, as well as doing the cybersecurity for it. And I fell in love with that aspect of it. I went and worked at Dragos for a while doing that. And now I'm out on my own because I really wanted to put hands on keyboards and help a lot of the water utilities. Because I remember doing a lot of assessments and be like, here's all your problems. And they're like, great, thanks. We can't do anything about it. And so why I started INC Secure, so I can go and hands-on keyboards help do some of this stuff. Today's talk is really about the worst case scenarios that we have, that in my opinion, that what I've seen, and some engineering mitigations to try to deal with those without cyber technology kind of stuff. And so from my experience, the state of cybersecurity in water, some things might be better than you think, and some things are probably as bad or worse than you think. And so I'm just kind of going to go through that as I talk. And this is just some examples. This is not a comprehensive deep dive. This is just some of the things. And I want to start off by talking about the primary mission of water and the main functions. And we do cybersecurity in critical infrastructure, not just to do cybersecurity. We do it to protect and add resilience to the fundamental mission that is there. And so that's maintaining pressure with sufficient volume of treated potable water, right? And so those things work together. If you think about on a high level how a water system works, we have intake, where we're drawing water either from ground wells or from surface water, rivers, reservoirs. We treat it, remove particulates, contaminants, disinfect it, get rid of the pathogens, do some pH adjustment for corrosion control, mine control with fluoride. And then maybe we have to move it long distances because maybe treatment and intake is here and then distribution is way over here. And so we have transmission, not always. And then distribution is where the rubber hits the road, right? So that's when we take that water and distribute it to the consumers, the businesses, the other critical infrastructure dependencies that Andy was talking about. And so those are the missions, and that's what we have to focus our cybersecurity controls on protecting. And so I like to talk about, how can we do that without technology and with engineering. So this slide is basically some of the worst case scenarios. So one of the ones I always go back to is rendering through cyber means the water chemically unsafe to drink. The treatment processes involve a lot of chemicals, not always, but oftentimes they're fully automated and you can consider a scenario where adversary could gain unauthorized access, manipulate the treatment processes, take those treatment chemicals out of scope and start to make the water unsafe to drink. So that's number one. Number two would be using the hydraulic components, that's pumps and valves, to affect the way water flows in the system. Like Josh was talking about water hammer overpressurization. If you think about 8 pounds per gallon of water and a whole bunch of water moving fairly quickly, and then you change that direction, there's a ton of momentum and it can break the pipes. You can have vacuum, which can, crush pipes or destroy a vessel. And so there are these sort of hydraulic issues that are potentially there, not always, right? So we have to look system by system. We have to prioritize where those exist. I have seen water utilities that draw water out of the ground, they pump it to a tank, and there's literally no way you can cause an overpressurization or a pipe break. I've seen water utilities where the flow meter, which is pacing the chemicals, goes right to the metering pump, not involved in the automation. There's literally no way you can overdose. Then there are water utilities that have the other situation where the circuit breakers and the variable frequency drives are on the same network that the operator is going to Facebook from. And so not a good situation. And so we think about that, and then we think about critical dependencies, like if you had this break at the same time there was a fire, or your inability with cascading effects not to be able to feed reliable, safe water to, sanitation, to fire, all the stuff that's been talked about all day. I don't need to talk about that. And the bottom stuff, yeah, it can happen. And it's, you can have temporary disruptions, you can have ransomware, maybe will not cause a unacceptable loss of the primary mission for an extended period of time, because you can recover from those things potentially quicker than something broken, right? And I don't want to minimize the bottom line, erosion of public confidence. If the public feels that the water is unsafe to drink and not reliable, that has, cascading effects too. And so I want to focus on, that. So this slide all of a sudden looks totally weird, but I'm going to go through it anyway. This is going back to that. It's better than you think. It's not as, or it's worse than you think, right? And so some comforting things is these systems are generally designed to be fairly resilient. There's lots of redundancies. They have oftentimes have multiple sources of intake, multiple sources of treatment, the redundant paths in the distribution system, emergency interconnects to adjacent systems. Everything's different. Like Josh said, you've seen one hospital, you've seen one hospital, you've seen one water system, and you've seen one water system. So they always vary, but they are designed to be resilient. The operators are generally trained to respond to failures and to problems, and they are out there and are good at this kind of stuff. Now, they're not trained to deal with cyber stuff, but it's in their mindset to do what that needs to be done to hamper along and make the system, get the systems back online in failures, and they do it pretty well. And the last one there, feasible to operate manually. I stuck an asterisk on there because some systems are and some systems aren't, and it's more or less, it can be a complicated thing to say. However, the way these control systems are built is there's oftentimes some resilience. If there's a failure or a loss due to cyber or other failure mode, water systems can be, made to function in some way. And I'll talk a little bit about that in some later slides. On the negative side, as we all have talked about, there is no regulation. So oftentimes you find low or no cyber protections in place. When we do find it, it's because we're lucky that there's somebody at the organization who recognizes there's a problem, and so they're a champion of the cause and they can get the funding or get internal staff or somehow deal with it. But in general, by and large, there's nothing there, as well as in general, by and large, there's sort of a lack of understanding of the risk. I can't tell you how many times I talk to people in water treatment plants who have no idea that, Muleshoe happened and the cyber army of Russia reborn and, hacked this, or, cyber avengers did what they did. People just don't know that there's a risk. And so they're going along and they're generally non-technical. So that's kind of like, so there's no protections, a lack of understanding, and however, they have some innate sort of resilience. So I don't think it's that big of a jump, to be totally honest. I think this is a solvable problem with the right prioritization and the right focus, and I'm hoping, we can do this. Going back to these cases I talked about earlier, these worst case scenarios, I want to talk about using engineering, not technology, to try to solve them, because I find in a lot of the water utilities that are non-technical with very little funding, as you start to add cybersecurity technology, it's a challenge to maintain that. It actually can make matters worse, right? MFA is not working again. We can't get on the VPN, and now they can't do their work because we put cybersecurity stuff in there that doesn't work because it's technology and it breaks. So let's try to, we have to do that, but we also need to really think about those worst case mitigations. So a long time ago, when I met Kevin Morley, I was, the EPA invited a bunch of water utilities, American Water Works and several others, to think about research projects to add cyber resilience into water. And I remember this was, I don't know, sometime in the 2010s, 2008, I don't know. But there were a bunch of us talking about exactly what I'm going to talk about. We knew that there was a cyber risk. We really didn't know much about what that looked like, how we would get hacked, what would be hacked, how would even detect that we were hacked. But we knew that we could look at the functional operation of water systems and try to use the engineering to mitigate the risks. And that's what I'm going to talk about. And then in 2018, Andy Bachman of Idaho National Labs came out with this article, the green one up here, talked about CCE and this approach to engineering out the biggest risks. And I was like, this is amazing. And then that got turned into INL's CCE and CIE programs, which I would encourage folks to pay attention to that. I'm actually not a CIE trained person, but I'm a control systems engineer, so I've been doing this. They have done a really good job of taking these concepts and turning it into a program that I think we can use. Ginger's going to talk about that tomorrow. So I do what I call cyber physical safety systems because I'm not like a CCE trained person, but it's kind of the same thing. And the concept is generally to apply a simple protective system to prevent unintentional or intentional physical damage by cyber attackers, right? So you get a side benefit to these processes self-limit the worst case scenarios. It doesn't, the nice thing about it is you don't have to be a cybersecurity expert. You're not using technology, you're using control system design and implementation. You can apply it to retrofit existing systems, and you can design it into new systems. The last one here is really important. We can't put in these systems in a way that we're not carefully implementing them, so you end up causing a problem. Like, this may never happen, right? We may never get hacked and get taken down, so we can't put in a protection for that then causes the problem, right? So that's a really important aspect of building these things out. So if you're going to try to do this, take that into as a primary design objective. So couple examples of one. So this one here is one we implemented where we had at MWRA, we have like lots of systems, lots of different pressure zones. We serve 2.5 million people. We had one specific area that we knew whenever the operators like turned a valve or turned on a pump, they were like, we knew that there were old pipes that they were afraid of breaking them. We had multiple big pumps and we said, hey, if all those pumps ever turned on by accident or maliciously, what would happen? And we thought it would break. We went, we did some hydraulic modeling and we're like, yeah, this would be bad. And so you see this, you see the green little box there, that's a pressure switch. It's on the downstream side of the pump. And so we set it to a pressure just higher than you'd ever expect, the system to need. And each pump of the 5 pumps had one of these. And so that was wired directly to the pump control mechanism, not through the automation, nothing on the network, just a hardwired signal. And when that tripped, the pump was shut off, had to be locally reset. It sent an alarm to the operators to know that this system engaged. But this provided a self-limiting mechanism so that if a mistake happened, somebody was programming the PLC and turned all the pumps on, or somebody tried to maliciously turn them all on, it would self-limit. So that's an example of, something to control for overpressurization kind of situation. This has happened. I mean, City of Wichita had a power loss. All their pumps went down. When power came back on, they turned them all back on and they broke a main, right? That kind of stuff happens just naturally. So it certainly can happen maliciously. Another example of hydraulics. Oh, no, I mean, this is like, $1,000. You could probably put this whole system in, under $10,000, I would imagine. It depends. Everything's different, but, you have wire conduit, a small pressure switch, maybe a relay panel, and some electrician to wire this in. So not complicated, not hard, not expensive. I say that, and then somebody's going to be like, it cost $100,000, but it's always different. So this one is another one. So we talked about pumps, right? The other thing we use to manipulate flow in pipes is valves, right? And when you see an operator move a valve, or the way we program the automation to move a valve is it's very slow and very careful so it doesn't make changes too fast. That is great. However, oftentimes we find that the actuators, so valves move with actuators. They have gears in them and electric motors, and they slowly move the valve. Sometimes the actuators are geared so that even though the operator moves it slowly, the valve could slam, right? And so If the valve slammed, that could create enough of a water hammer or a pressurization to break a pipe. And so one way to self-limit is to identify where these valves move too fast, adjust the gearing so that the valve only moves about as fast as you'd ever need it in an emergency situation, and it self-limits. The next bullet here is a rupture disc. That's like a sacrificial element. So there, sometimes, you may have like a specific situation where water levels could change quickly and pressures could spike in a given like contained area. And so you design in a sacrificial element like a rupture disc, so you know where the break is going to happen, so you can fix it, and you're not going to have to go looking for a break somewhere where you don't want it to be. And so just another example of dealing with self-limiting hydraulic engineering stuff. This one is around chemical overdose. And so this is an example of sodium hydroxide. We use it for pH adjustment, oftentimes for corrosion control and other things. And what we do is we raise the pH in the automation, right? And so we have a set point of how many milligrams per liter of sodium hydroxide we want to put in. We measure the flow of the water, and everything just kind of tracks along. And then we have a pH transmitter, which is down at the bottom corner there, and that kind of tells us what the pH is. And we can set alarms. Now, assuming a capable adversary is able to get into the automation and manipulate this, they could overdose. However, this little system, if you see, I have a red line coming off that little round pH transmitter. Those often have like a built-in relay that says, oh, pH is too high. It'll close a contact, sends it to a relay panel, hardwired signal to shut down the feed pump, and then you've self-limited the overdose problem. You also send a connection, send an alert back to the operations staff that, hey, this system has kicked in and you need to go investigate what's going on and reset it. It's just another example of, a way to take some of the like high risk consequences off the table. Another example, where am I at with time, Josh?
Theory, 7 more minutes.
Oh, good. All right. Cool. I'm good. So this one is in the little picture is an ozone generator, right? So sometimes in treatment plants, we have complicated pieces of equipment. We buy them in self-contained units from ozone vendor. In this case, they bring it to our plant, they set it in, and they connect it up. If those don't come off the shelf, so if that thing was destroyed through some sort of cyber brick, you'd have a hard time getting that back online. So I advocate when you have a critical skid system that you can't live without like that, instead of connecting it to your process control network where somebody could reach it by taking unauthorized access, you hardwire your signals from that to your main PLC so that you get enough data and you can control it, but it's not totally exposed to being destroyed long-term. This is like one of the key fundamentals of CCE that I remember is like, those critical pieces of equipment that would be months to replace, you got to take a different approach to how you connect them in so you get enough data, you can control it enough, but it's not exposed. So that's another example. And this next one is, a lot of times we can build these systems in a way that we can maintain some local or manual or hand or even local automatic operation so that, it's not ideal. You don't get all the diagnostics, you don't get all of the information, but the system can run autonomously when there's a failure or a loss of your primary control, so that you can limp along while you recover and you can maintain that primary mission of pressure, volume, treatment. Hopefully treatment's a hard one in manual, but the local auto thing can work in treatment. So just those are some examples. This last one I'll just cover really quickly. Like, this isn't a protection, but in water where we have a luxury, sometimes processes are fairly slow. And so, sometimes just getting an indication of a problem is a good thing. And so if we think about if somebody was manipulating your control system and masking what they're doing so everything looks fine, but it's not, you can add in independent monitoring solutions at various points at key process parameters to send you an alert that say, hey, your system says flow is here, but it's actually there. Your tank's low, even though your SCADA screen's telling you it's normal. So it's just a sort of a additional level of situational awareness. Sometimes, in some cases, this may be a nice solution for you. What's that? No, I think I put one of these in for like $2,500 the other day for somebody. So, I mean, there is a cell, they have a cell connection, so there's an ongoing cost there, but the thing itself is pretty cheap. So, I think that's it. I'm happy to take any questions or, if anybody has any. Yes.
So famously, they had the fire alarm, and the guards saw it and were just kind of looking at it like, "Why is this going?" You set up processes when you install these as well, so they know it's not just, "Oh, that's a funny red light."
Yeah, absolutely. That is a really important thing. When we put training is huge, right? And so this thing's probably never going to go off. So 10 years from now, when that pressure switch trips, are they going to know what to do? So yes, it's the training and documenting what this thing is for is key for sure.
So there's a process where you're mapping out how this system, like what connections, because you saw a process map of showing the independent alarm system. Is that a common thing that you do when you're going in for an assessment? You go, okay, how do I make sure that this is engineered in a way that would not fail? Like,
yeah,
what's that process?
That is a great question. And the way, like for that example, we went through every single facility and looked we had the right team. We had the operations team, we had the SCADA people, we had somebody who had awareness of, what kind of OT cyber attacks are there. And we went through on a system by system basis and identified, vulnerabilities and through an engineering design process and so it's not simple. It's not, that process is not simple, but once you get to you have a playbook of things you can apply,
The solution is simple. Or that pressure sensor where it was just trying to prevent overpressure and you just directly connected it to the power switch. That's brilliant. And so like making sure that you always do that simple solution, that's a hard process.
I think initially, yes, it takes some engineering, but I think you can get to a point where you can see it, with trained folks, Yes, Josh.
Unless someone else is over there, please repeat my question to the mic. You had the asterisk, and I've encountered quite a few communities that don't want to be connected, but some of their supply chain is kind of pushing them into connectivity. How do we maybe guide people that if they're not yet connected to the internet and exposed, or if they're making choices about when to do more connectivity? Like, can we educate not to throttle our purchasing and architecture decisions as we modernize? Like, is there advice or triage?
So you were asking about when people are deciding to connect to the network for efficiency or for cost savings, like how can we sort of talk? Yeah, totally, like a value engineering. So, you may have a design, and I saw this a lot back when you do a design where you had an automated control system, but you still had a control panel with switches and buttons and displays, and you go through a value engineering process and they'd be like, oh, that's going to cost money. Let's take that out of there. I recommend not doing that for this reason, like maintain that resiliency. It doesn't cost that much more, how can we educate people? I guess it's, I don't know.
We want to change the subject. I was going to jump on that. So some of the suppliers, and you've probably seen this, right? You don't have a choice, right? I'm going to buy Dr. Pepper. It's going to come like this, and it doesn't. I got to connect to the internet to open the can, because that's the only way to open the can. There used to be the full tank. The full tank's been removed. So I don't have a choice. Right? I mean,
it's true.
It is, and utilities don't change assets all that frequently, and so in terms of market influence, it comes back to secure by design.
It's driven by the engineers, absolutely.
So I guess I sort of have some answers in mind, but not one yours. You heard the secure by design panel today, they're thinking you need IT.
Right, no, this is.
You hear that there's congressional staffers listening to the stream right now.
Yes.
I almost wonder if like, there should be a requirement to have annual operations
Well,
for the next six.
That's
Not
gonna
for
be
you.
really complicated for certain treatment processes, being required. Yeah.
I don't think
It's not a manual process.
it's too specific. You need,
Membranes, ion exchange, that's a heavily automated.
I guess my
manual version.
rhetorical clip is whether it's right now or a week from now, like, if we were to ideate, what is the right balance between introducing that new risk? And like, I don't think we realize how much we're introducing that.
I think that's the point. There has to be some sort of risk calculation that includes cyber in the design, and the solution is going to vary. You know, we can't mandate a solution that's going to be wrong.
Two things, but I want to jump on this just a little bit because we recently had this conversation. So manual is not always the solution. You just cannot assume manual. When regulators or standards bodies come out and say, thou shalt do X, PFAS is a great example, or other things. In this region, we have the Gulf area watershed policy. There are a variety of things that come out. Let's just say, for argument's sake, EPA says PFAS limits are X. You have to meet your treatment requirements. That requires technology in order to meet that. And there has to be thought that's given to what level of automation is required to meet those standards. And if you cannot do that in a manual operation, then forget it. So that's my first thing. The second thing I just wanted to bring up, so your engineering design controls, always good stuff. There is a care and feeding that goes along with that. It is not a one and done. If you put a system in that never fires because you properly operate your system and you need it to fire on that one occasion, you have to put systems in place to make sure that it works. Operation program, testing regimen, whatever it is. I'm curious as to the folks that you've worked with, what has their thought been on adoption of those programs, especially if they don't make sense?
Great point. So we have, you have Maximo or other things like that, where an operator has a work order periodically every 6 months, run the station in manual, trip the alarm, make sure it comes in, all that stuff. If you don't do that, when you're relying on something 10 years, it never kicks in. And then finally you need it and it no longer works because the corrosion has ruined the terminals and the contact is made, but doesn't get anywhere.
Squirrels.
Yeah, squirrels eat the wires. Right, you have to test it. All of this does. But if you put in a firewall, that needs care and maintenance too. If you put in a SIM, it costs $100,000. You're not going to set that and forget it either, So
Fire suppression needs testing.
exactly. Oh, thank you.
All right, can we thank Gus for rounding up the day?